Good afternoon to everybody. My name is Marlene Luckner. I'm the marketing manager from Arkham Systemautomation, and I wish you a warm welcome to our webinar about Simcenter. As an innovative company, Arkham is supporting its customers since 1994, primarily in the areas of product development and manufacturing. Arkham offers integrated solutions that cover all phases of the product lifecycle. As partner with the Smart Expert status, as partner with the Smart Expert status from Siemens Digital Industries, we have round about 40 employees at 3 locations in Austria. And do not only offer you the extensive portfolio for software and hardware from Siemens, on top we propose services from professionals who support you or can do the simulation and testing for you. Arkham Systemautomation and its subsidiary Arkham Engineering are the perfect combination between software, hardware, and service provider. So, and now please welcome David Sulchuk to the presentation of thermal characterization of semiconductors. It's your turn, David.
Thank you for the introduction, Marlene. You probably see me in a very small window size, so if you want to have a larger window, you can switch the spotlight view with the right click. So hopefully everybody see the presentation now. I'm going to talk about the thermal characterization of semiconductors. My name is David Sulchuk, and I'm responsible for the thermal characterization and power cycling in Europe. I taking care of customers in semiconductor industry and also automotive and various industries. So the agenda today, I would like to give you a short introduction about the thermal transient testing. How does it work? Then I cover how our measurement technology works a little bit deeper how to interpret the result. And then I'm going to cover the thermal quality testing, in-line testing solutions. And I will talk about the reliability testing and power cycling options. At the end, I would like to introduce a workflow to improve the accuracy of the lifetime estimation of power modules. So let me continue with this slide. It's a little bit of motivation. How can we get along with issues in power electronics? We have many various error sources. You see pollution, air, dust, and radiation. These are typical error sources of the power electronics. And of course, also on the top, you see the temperature related issues. These are the most common issues, actually. And I would like to talk about a little bit deeper about that topic, because as the power density is increasing in power electronics, we have to focus more and more on thermal performance and thermal management. And this study shows very well these are the votes for the various error sources among different industries. And we see that these temperature-related issues have the highest vote among these error sources. So, yeah, we have to focus more and more on thermal performance. And these are our product portfolios, product groups. how we focus on thermal management and thermal characterization. So the first product group is here, so-called the 3-step. This is a thermal transient tester tool, which covers mainly customers in working in laboratory, R&D department, product creation. This is just responsible for thermal characterization, basically thermal resistance measurement, and a little bit more. I will talk about that later. A similar product is the power tester here. This is a reliability tester carrying out active power cycling. This is a combination of power cycling and this 3-step measurement, thermal transient tester measurement. So as the reliability test goes on, we get information about the structure, about the semiconductor by carrying out measurements with the 3-step parallelly. So these measurements can go on maybe for a year, so it's very important to have an automated tool for that. I will talk about that as well. And on the bottom, for the production line, production layer in this pyramid, we can install a tester next to the manufacturing line to have a very quick decision if we have a quality issue in that particular semiconductor or setup, and we can sort out and have a very quick decision of go or no go. So this is the link between a robotic arm and the 3-step thermal transient tester. Let me start a little bit about the measurement technology and what is behind that. So if I mention thermal resistance measurement, you immediately think about temperature measurement, and this is correct. We have to measure somehow the temperature, but this is not that easy because there are many various options here, and some of the options are not very good. So one of these options is the thermocouple. Thermocouple is a great solution because it's easy to use. You get information immediately, but only from one single point from the surface of the semiconductor. And as you see here, the temperature distribution is not homogeneous on the surface of the semiconductor package or on the chip surface. This is a very serious issue for the thermocouple measurement because you don't really know where to place your thermocouple. A little bit on the left, a little bit on the right, and your temperature value is totally different. And of course, there's another source of issue here, and this is the influence of the thermocouple itself. So the thermocouple cools down the surface of the semiconductor package. As you see on the picture, 39 degrees Celsius under the thermocouple, and a little bit on the left, it's already a little bit higher. So that's not a good solution. The thermal camera, it's better because we get information from the surface. That's not just one point, but we still don't know what is under the surface. So it's still not the best. And we have here also repeatability issues because even if you paint everything black on the surface of the device, you get some issue from the environment. It creates some error in your measurement and repeatability problems. So this is again not the best. What we prefer is the electrical test method. This is a standardized methodology, repeatable, and we use the semiconductor itself as a temperature sensor. So you see a diode here. The diode has a certain temperature sensitivity, and it can create a perfect temperature sensor for us. And we don't have to measure directly the temperature. We can capture electrical signal. How does it work? We need 3 steps. The first is to find a temperature sensitive parameter. So let's stick to this example. You see this diode here. We have some current source, which is the sensor current. So some current flowing through on this diode. So obviously we have a voltage drop on that diode. And this voltage signal is temperature dependent. The higher the temperature, the lower this voltage signal. It has a negative temperature dependency. This is the curve. This is the voltage temperature relationship. So higher the temperature, lower the voltage. We get this calibration curve after that. This has around 2 millivolt per Kelvin for a diode. And it allows us to calculate the voltage signal back to the chip temperature. Because what we do, we put this diode in a temperature controlled environment, heat it up during this calibration process from 20, 30, 40, and so on degrees Celsius. We capture these points, what you can see here. And then we get some voltage signal from the diode, maybe during the measurement. So we can calculate back to the junction temperature by using this equation. So this is how we measure the chip temperature. And of course, we have the methodology to measure the chip temperature. Now, what we have to do is to create some measurement. This is the third step. Heat up this semiconductor package and capture the response function on that. This response function is a voltage over time function, and this will allow us to get junction temperature change over time. So this is a short example. How does it work? So you see two current generators are activated. So this is one for the heating current. This is typically a higher, like maybe 100 amp. And you have also the cooling generator here. This is maximum 1 amp. And we have a diode, which is the sample. The diode should be tested here. We capture the voltage signal on this diode. And we have the typical curves for a diode. So you see the voltage current diagram here and the workflow with 4 points. So we have a blue and a red curve here. The blue curve is the cold state. As I already mentioned, the higher the temperature, the lower the voltage. So we see a little bit different position for the hot curve. And we started on room temperature, which is considered as a cold temperature. First step, we heat up this diode. Between the first and the second point, both current generators are activated. So you can see that the device is heating up between the two curves. And then sudden switch, it's required to switch off the heating current generator. And between the fourth and the third point, we capture the cooling curve as a response function on this device. This is a voltage over time function. And this will be the base of the further investigation of the thermal performance. This voltage over time function. As I mentioned, we calculate this back to junction temperature change over time. And I will show you what we can do with this information. So the next step is to use this function, and we use it for a so-called structure function. This is one way to use that information. I have to jump over all the mathematics here to save time, but this is well published by the colleagues in IEEE paper. You can find a description how we get to the structure function. So this is basically a one-dimensional heat path. So you see a typical semiconductor package here on a cold plate. This is like a kind of sandwich structure. So you see the chip, a base, cold plate. The top of the chip is the heat source. This will be heated during this measurement process, and the heat comes down in the direction of the cold plate as the measurement goes on. And during the cooling phase, we reach the ambient or cold tail temperature on the top of the junction as well. So this is the whole measurement process, and during this the heat penetrates in these layers, and we get a one-dimensional heat path from junction to the direction of cold plate, and we can set up a thermal resistance and thermal capacitance chain along this path. So this is a vertical movement from the junction to the cold plate. As we walk along this heat path, we start with the chip here on the left. This is a thermal resistance and thermal capacitance diagram. The chip has, this is the first layer, and it has a relatively low thermal resistance. So you see a certain steepness goes up. Then the steepness change. We have a sharp edge here, almost horizontal layer, which is the first thing. This is the diode edge, relatively high thermal resistance and low thermal capacitance. Then again, steepness change. This is a copper base. And again and again, and at the end, we go vertically straight up in the air. This is the cold plate. And the cold plate has infinite thermal capacitance, including the environment and the laboratory where we carry out the measurement. So that will go into the singularity, in the infinity. This was a theoretical example. Now I show you a real example. This is a real measured curve on an IGBT. And the IGBT has this setup, cross sections, IGBT die attach copper, solder, and so on. See the sections here. And these are the material layers. So these are the physical layers in the structure function view. So you see the thermal capacitance, thermal resistance diagram. We start with, again, with the die attach, with the die attach, the copper, and so on. And you probably see that the layers are not that sharp as it was before, because these edges are theoretical. In reality, the isothermal surfaces are not parallel with the physical layer, the physical borders of these materials. So we don't get these sharp edges as before. It's a little bit murky between the layer borders, but we can still see some steepness change, and it allows us to identify the physical layers. So it's very important to highlight that we not just get information from the chip or from the semiconductor, we get information from the entire heat path, including the heat sink. And let me show you a little bit of game here about that structure function. So we start with the measurement. This is this sandwich-like structure on the left. You see we heat up this semiconductor. This is a simulation example. And we capture the cooling curve of this device. But there's a trick here. We measured two curves. One sample had voids in the die attach, so some air bubbles and some lack of die attach material, and the other one has no voids. So this is it has a perfect quality in the die attach. And what we see here is the temperature over time in the logarithmic time scale. So this is the response function. Of course, you see an increasing function. You can invert it. Heating or cooling doesn't really matter. The point here is to see in the temperature over time curve, this is not really visible. I plotted both curves, and you can't see anything. These curves are completely identical. They are top of each other. If you are the engineer who has to decide which one has voids inside or which one has no voids, then you have trouble here. There must be a better way to see that, and this is the structure function. The structure function allows, this is the same information from this temperature over time curve. We were able to transfer it to the structure function U. And you see the two curves are separating right after the die attach. So we see the chip, and in the die attach, which is the first horizontal layer here, or not horizontal, but almost plateau-like layer, the red curve is a little bit shifted on the right. That means the thermal resistance, the Kelvin per watt value, is a little bit higher for the red. That means this is the void measurement. The other one has no voids. So same information, but different plot, and we see much better the where is the issue in the structure, not just the total thermal resistance, but also the really the layer, and what is the difference between the thermal resistances. This is also very important information. Another example, a typical use case to have the requirement to measure the junction to case thermal resistance. So from the top of the chip to the bottom of the package, the case. What is the thermal resistance? This is a data sheet information, but many customers don't trust in the data sheet value. They want to measure it. And this is the methodology to do that. We carry out two measurements, the same sample, put this sample on a cold plate, and put some thermal grease between the package and the cold plate. Then repeat the measurement without thermal grease and compare them. And what you see is a separation point here. Separation point right after this value of 1.0 maybe Kelvin per watt. Because up to this point, everything is the same. The thermal structure is the same, but from this point, we have a changed interface layer that creates a higher thermal resistance for the dry surface. This is the black, and the blue one has high conductivity. Or you can create this with high conductive or low conductive thermal interface material. You get the same information. Another example is this is where we can't use the structure function. We use a little bit different information, the so-called ZTH curve. This is a Kelvin per watt value over time in a logarithmic time scale. So how we get this? We just normalize that curve, the temperature change over time, with the power. And where we use it, we can use it everywhere. But this is a special case where we can't use a structure function, only this one. If we heat up one chip on the PCB maybe, and measure the other one. And between these two chips, we have a thermal coupling. This thermal transfer can be measured. Maybe you can imagine a half bridge. High side is heated, low side is measured. And you can set up the whole heat map, the ZTH or thermal impedance map of this module. So if you measure power modules, this is a great way to do that. Another use case is to compare the structure function with different aging states. So I already mentioned the reliability test, where we have the power tester do some active power cycling, and we plot the structure function in every maybe 5,000 cycle. You can see here until 15,000 cycle, these are the cycle numbers. You can't see any change. The plots are perfectly on top of each other. But from that point, 20,000 cycle, this here, we see a right shift. And after that, it's up to 35,000 plotted. It's completely shifted on the right. So it almost burned completely that die attach. And of course, the whole package burned out after that. So during this reliability test, we just we don't get just the information, the cycle to failure. So how many cycles do we need to fail this device? But we also see where is the problem and we can identify the weak points. Let me show you a different topic. We were talking about structure function. How great is that and how useful was that? And there's a process where we can use it along with other interesting features. So you want to improve the thermal performance of a setup and improve the quality. We have a workflow, so you need some thermal characterization with the tristor. You get the structure function and you see the thermal performance of that setup. This information can be used in some kind of simulation model. So you can build up your simulation tool, simulation model where you use structure function and define some parameters for manufacturing inline tester, where we can sort out which is actually the package where we fulfill the requirements and which one can't fulfill. So which has low quality and high quality. So sort this out, and then we can fine-tune this process, improve the quality, and as a feedback loop, we can fine-tune that model and use some other parameters. So how does it work? It's not just for a semiconductor manufacturing company. Everybody basically, you build your own product using third-party semiconductors, then you rely on datasheet parameters and the quality of that MOSFET in that example. So you want to mount that MOSFET on a PCB and on a heatsink. Maybe you have some solder bubbles, and there's another issue, chip size difference or die attach counterfeit. So many various quality issues, and you can use the structure function U or the ZTH curve to get all this information. Where are the problems? And we can use it for with a manual handler, a robotic arm, to find which one should go from the manufacturing line and which one can stay. So this is our example demonstration where we see a robotic arm, we see the tristor and the software for that. The software has a reference data, a reference curve with some threshold. And these are the different parameters where the robotic arm sorts out the die attach, high quality, low quality, absolute no-go maybe. So put this package on a heatsink. It's a slower video for demonstration. It can be also even in 1-2 seconds, the whole process, or even shorter. It depends on the measurement type that we need. And we have also other robotic arms, so not just a typical arm, but also a line tester. So we have to set up some parameters for this MOSFET, the datasheet parameters, and then we need to create a project where we, or the engineer, we have engineer surface on that software and operator surface. The engineer surface can define the parameters for this test, and we have the reference curve, choose the right project and start the measurement. So the robotic arm can put this on the cold plate. It's a printed circuit board connected for the measurement wires. That was the measurement. And now we go back to the next sample. So at the end, we can sort this out, which one is the right quality and which one has not sufficient quality. So we have also an automated process for the reliability testing. That was all about the thermal characterization. And now I choose a to present a little bit different approach where we have normally in the automotive industry this requirement to improve the lifetime estimation of a certain inverter, and I show you a workflow here. So what is power cycling? Power cycling is there are active and passive power cycling. Active power cycling where we take this semiconductor and use high current to heat this up. We have an on pulse and we have an off state where the current is not flowing through this device, so the device cools down. So we have this is one cycle. This is the simulation. And it goes on for maybe a year long, and eventually the device fails. There are different failure criteria. We are also a member of the AQG guideline. This is the European automotive guideline for semiconductor testing, and that defines two test methodologies. One is the PC-SEC, where we have a relatively short pulse time. This it has a focus on the first layers like die attach and bond wires. So this relative short pulse test these layers with a lower time constant. And then we have the PC min test, we have a little bit longer time range, and then we can go to the next layers like maybe the substrate. So we have the two test methodologies, guidelines. Now we need some equipment to do the job. And there are many options. What we see sometimes is a process where we take this IGBT in this example, start the power cycling test on the test bench, and wait until something happens. Maybe the voltage start to increase, or you don't know really what's happening, but after a while you want to test it, so you remove it from that test bench, bring it to the lab, and under microscope you can examine the failure type and the degradation on that device. So you build up again the test bench because the test should carry on, and hopefully you put it the way back as it was before. Normally this is not the case, because if you use thermal grease, it's very, very complicated to reach the same total RTH, the total thermal resistance of this setup again. To put this back, start again and repeat the same process, maybe a year long, and you need an operator in front of that tester. So it's really time consuming, and of course, if I mention time consuming process, that it costs money. You can't really repeat it professionally because you can't build the way it was built in the bench before, as you remove it from the test bench and bring to the lab. So these are error sources, and makes your measurement not accurate enough. So need some automatization and some combination of checking the degradation on the device and the test. And this is our solution. This piano-shaped power tester is one of our power tester equipment. I will talk about that later. This is a closed environment automated test process. We mount this module on the cold plate, fix it with holders, with a fixture, use maybe some thermal grease, start the measurement process, and we don't have to touch that module for maybe this year, for the year, because it goes automatically. It captures the data on that IGBT, what is going on, if it's bond wire issue or the thermal performance is getting worse and worse. So you get real-time information about that degradation process. You can download the data from the power tester. You can check it remotely. You don't need an operator next to the power tester. It goes automatically, and once it is finished, we can download the data and use it for further tests. So this is the best way to do that. And additionally, which is very important, it's the industrial environment. So we have various safety features: smoke detectors, temperature sensors, leakage sensors. This is very important because what I normally see if I take a look at the self-built equipments in laboratory, there's one guide built that power tester many years ago, and this is the only person who knows how to repair the power tester, and it's not industrial, and there's no support for that. This is a huge issue, and if this person leaves the company, then nobody can do anything with the equipment. This is different in the industrial equipment, where we have a support team. We can help out, go on site, repair if it's required, and get software updates. So this is how it looks like. Let me show a short video. So there are also another power tester which looks like tower, 2 cold plates inside that. So it's covered with a plastic bulletproof coverage, and we have also curves for structure function, but various other curves like delta junction temperature, maximum junction temperature, and so on. So this is the example that I showed you. The structure function plots as the cycle goes on, so you can get all this information. So how the measurement starts, we have to define the sample, if it's IGBT MOSFET, what's the measurement type, check the datasheet parameter for that, and this is most common measurement mode for silicon carbide, which is for power modules required. So we can support all the AQG guidelines for that, and yeah, it's easy to fix the device, to mount it on the cold plate. We have this rail system, so you can find a position for the modules easily, and use the torque key to push from the top to the cold plate. So we have different requirements, various industries, from automotive to power applications, or maybe solar power or wind power, or railway traction application requires, of course, higher power. So we have a smaller device which starts with 600 amp up to 3.6 kilo amp. And also there are customers requiring the testing environment. This is the piano shape where we have the cold plates, and of course there are other requirements where we don't have to sell the cold plate as well. We just sell the measurement technology. These are the tower shaped devices. And this is an example again how to use this for an automotive example. So you have a hybrid or electric car with an inverter inside that car, and there are so-called driving profiles. It means there are more aggressive drivers, so the speed goes up rapidly and then drops down. we know these type of drivers, and there are calm drivers as well, so the speed is relatively flat over time. And these driving profiles, this is the input data for this lifetime estimation workflow. And this is what I will show you, what we can do with that. So this data goes to the simulation model. The simulation model, some kind of CFD model or finite element method, calculates the temperature histogram, which is the temperature change on these inverter modules over time. And that means we have 100 degrees Celsius temperature change, and that counts. Maybe we had 100 degree, from 100 degree we had 5, we had delta T 50 degree, that was maybe 20, and we had maybe 20 degrees Celsius change, and we had from that maybe 150. So we have, this is the temperature histogram, and that information goes to the testing as well. So we have the power cycling test methodology, take this IGBT and do the test until it fails. And the test criteria for that IGBT test comes from this data, this temperature histogram, because delta T that we need to reach with the power tester should come from that temperature histogram. And there are many problems with that. So, at the end, you expect to get data with this curve. These are the lifetime curves, and the IGBT has maybe 20 or 12 years of lifetime. There are various equations that give you that value from that lifetime curve. But what you can see immediately here in that workflow, that it depends on the temperature heavily. So the lifetime calculation has this temperature dependency, and that means we have to have the highest possible accuracy for that data. And this is the first problem, how we get that. So we see here two setups. One is calibrated, the other one is not calibrated. The temperature distribution is totally different. What does it mean? If you use simulation model, you have the problem of garbage in, garbage out, because you don't really know what is the material parameter for that semiconductor. Even if you get it from the manufacturer, you don't know if there's maybe a small air gap, or is there any quality issue in the certain layers, and you don't know the thermal conductivity for these layers. Sometimes you don't even know the geometry, the thickness of the layers, or you don't know the material of the layers. So there are question marks here. That's why we call it best guess model. And this best guess model can be very good, but most of the time it's far from the reality. What you see here, this is the simulation between the best guess model and the actual calibrated model. What does it mean, calibrated model? You see the two structure functions here. The two structure function, the red and the blue. The red was the actual measurement. The blue one was the simulation, which was calculated from the best guess model. And what we see, the uncalibrated example, totally different. If we calibrate it, that means the simulation model will use the actual measurement data and adjust the material properties and the geometry. It's a semi-automated process. And then you get the perfect overlap between the curves. So that's how you can improve the accuracy of the simulation model. And this improves a lot, actually, and matters a lot, because maybe you think that for this example, we have a gap of 0.5 total RTH on the measured one. The simulated was 0.6 Kelvin per watt, or other way around. It's a huge gap, and that means maybe we have to carry out the power cycling, which you can see here. This is the temperature change over the cycle number for 120 or just 110 degrees Celsius. Just 10 degrees, it's not much, but in the semiconductor, that means it's an additional more almost 20,000 cycle, and 20,000 cycle, it's a huge error here. So that means with 110 degree, the semiconductor leaves 20,000 cycle more. So this is maybe a lifetime reduction if you have an error, a lifetime calculation error of 30%. So this is not acceptable. That's why we use our simulation tool called FlowTerm, and FlowTerm can do this semi-automated model calibration. What you see here, the second problem is with the power tester. That was already covered in the previous slide, that we need some automated process. So if you take a look at the workflow, this is one example here. It's one single IGBT. We need to test as many IGBTs as we can, because statistically, this is how can we improve the accuracy. So you see all these points here in the cycle to failure diagram. The different points are the actual test to failure informations. If we get more, we have a better fitting. So that also improves the accuracy, and we don't have to extrapolate it from 2 points. So that's thing. So just to sum up, 2 things. One is the simulation model with FlowTerm. We can calibrate it by using the data from power tester, Tristan. And the other one is the scalable and automated process of power cycling. So we get cycle to failure data for much more points. Okay. So before we go to your questions, I would like to show you a couple of stories from different customers, maybe one of your competitor even. So Yaskawa using Simcenter Tristan. This is for motor drives, and Tristan is the thermotransient tester. They can use it to improve the thermal performance of the power electronics inside that setup in Japan. So this can be also used for very small, tiny LEDs up to railway traction application power electronics, or even in your cell phone, the processor can be measured. So almost any size, it doesn't really matter. Important is to have an active semiconductor inside that. And we can get the information. Probably you know Infineon. This is a good example. I haven't mentioned that kind of setup. This is a Tristar basically connected with a special cold plate. We call it DINTIM because it's specialized for thermal interface material measurement. So instead of using thermocouples and other tools, there are various tools to measure the thermal conductivity of the thermal interface materials. We use the Tristar, and this is again highly accurate because we don't have to rely on thermocouples. It's repeatable. It has an excellent resolution and we can measure thermal greases, silicon pads, even metals. So we get the thermal conductivity for that particular sample, and it's very easy to use. So it's just we push the start button. Don't have to adjust anything during that measurement process. It just gives the measurement result. So fully automated process. Infineon used that one. Nottingham University is one of the great example to use the power tester for research and research purposes. It was one of the first power tester as the silicon carbide technology started to go from the research field to the industry. As we sold that power tester to Nottingham University, and they were using it for silicon carbide testing. And in that example, we see the IGBTs. This is Professor Mark Johnson has various papers about that, and they use it for beyond the borders of the power tester for wide bandgap measurements as well. So it's a very interesting topic. The value here is again not to use necessarily time-consuming microscopic analysis after or during the power cycling process, but using the power tester, trister, to get all this information during that measurement. Short example, Denso, automotive industry. They use since 2015 the combination of our simulation tool, Flowterm, and Trister to improve the thermal verification process, and they were able to use, of course, for cost reduction at the end. It's a very significant cost reduction of almost 80%. Another example from an LED company, we can provide LED measurement tool. This is also the Trister, and we combine it with optical measurements. So we have an integrating sphere for companies where they need to carry out this thermal characterization in the integrating sphere. We can provide that. But also there are companies where we already see an integrating sphere, so we integrated our measurement technology to use their integrating sphere. So this is also optimal to use it for simulation. And that project, the Delphi for LED project, it was a huge project involving many engineers from our side, and researchers, universities, and industries. It's worth to type it in Google and check it, because there are various papers available. It's really interesting. Okay, so thank you very much for your attention and time. If you have any question, please feel free to ask.
So David, currently no questions in the chat.
At the moment, we have no question, yes. But if you have any questions later on, please feel free to contact us. Are there any questions now? Not at the moment. Then I say thank you for your presentation, and I wish you a nice afternoon, evening, and goodbye to all of you.
Thank you.
Thank you, David.
Bye.